Hi, I'm going to take you through a little tour of the software project I built while I was doing research on molecular computers. What I have built here is a fully functional molecular computer that implements the Chemlambda model of computation. I built this over several months this year as I performed research on decentralized rewrite systems, specifically Chemlambda, as you might guess. I wanted to showcase some of the design choices I made while building this, because it seemed like a pretty good idea. My aim in creating Chemlambda-hask was to improve upon the initial codebase built by Marius Buliga, the project's founder and the person I did most of my research with. Chemlambda-hask is a completely modular implementation of Chemlambda designed to allow anyone to take the components I've developed and build upon them, both to explore Chemlambda as a whole and to also just to expand on the theory of molecular computers. So I'm going to take you through a little walkthrough of the modules of the project and just show you how everything's structured. So first we're going to look at the core. The core set of modules contains the most fundamental primitives for molecular computation as defined by Chemlambda. The great thing about core is that it's independent from Chemlambda as a whole, meaning that you can use the data structures I've created here, or not created, just implemented here to pretty much create a multitude of rewrite systems that aren't tied to Chemlambda overall. And I just want to take a minute to explain what I mean by that. Chemlambda works by encoding computations in directed graphs, which happens to be a great way of representing molecules, and rewriting them based on a set of simple rewrite procedures called moves, somewhat analogous to enzymes in a chemical reaction. A molecule representing a computation is comprised of what are called elementary molecules, which you can think of as sort of like atoms. When certain atoms, I'm using air quotes here, are bonded to each other, they react, leading to changes in only that part of the molecule which have the effect of stepping through the overall computation. Atoms connect to each other via their ports. Ports you'll see in the file in a second. They're kind of like valence electrons for this reason. Now all the code you're seeing here is written in a programming language called Haskell, and what I'm doing here is defining all the fundamental primitives and the behaviors they require in functions to do their jobs pretty much. This is essentially what the core is. It's just all the files describing the basic building blocks of a molecular computation. These are all things you're going to need. And here we're looking at nodes. Now, there's a pattern that comes up in Chemlambda pretty often, and it's combining atoms with ports. And the reason you do that is because every atom will have ports, and all ports will usually be associated with atoms. So nodes are just a data structure that pretty much pairs atoms and ports together so that you can talk about them together, which is often useful. Alright, now here we're going to look at adjacency lists. This adjacency lists are one way of implementing the graph data structure, which is again what we're using to implement molecules. Pretty much an adjacency list holds a list of nodes, which we just saw in the previous file, and all of their adjacencies, pretty much everything they connect to in the molecule. So that's why it's a really good way of describing graphs this way, because atoms naturally having ports, naturally having connections incoming and outgoing, this is a great way of just easily encoding that in a data structure. And now on to patterns. This is my favorite module in the core because I ran into a lot of problems while building it, and I was able to learn a lot of stuff about something called the subgraph isomorphism problem, and maybe I'll explain that in a little bit. But pretty much you use patterns to identify subsections of a graph based on some characteristic they have. Maybe you're looking for a certain bond between two atoms and you want to find every occurrence of that type of bond in a molecule. Patterns allow you to do that. And you can see here, this is all code I documented out that I might be able to salvage something from later. I can't tell you how many times I just rewrote this thing. I was trying to figure out why searching through parts of a graph was just so painfully slow. It was the bottleneck of my whole implementation at the time. So I figured out that it had to do with this thing called the subgraph isomorphism problem, which pretty much explains why searching through a graph is, well, the difficulty increases exponentially with the number of nodes in the graph. So I was kind of happy to figure that out. Alright, so now we're going to move on to the chemistry modules. This is the set of modules that pretty much defines Chemlambda's specific chemistry. In core, you're able to define a multitude of rewrite systems because the core is so general. It doesn't require Chemlambda's chemistry to work. So we can use what core provides us, all those primitives we define, to make specific chemistry, specific rewrite systems. And that's what we're doing here. The generalized idea of a pattern we defined in core, we're now using that to define the specific patterns that Chemlambda looks for in a graph. And with patterns, we have these things called moves. And moves are pretty much what you do to a graph or a part of a graph once you've identified a certain pattern in it. So let's say I find a certain atom connected to another atom in a graph. A move describes what I'm going to replace that with based on Chemlambda specific chemistry. And again, anyone can build another rewrite system that follows different rules. They don't have to follow this set of rules right here. And you can see here that each move corresponds to an actual pattern. All the names are similar because each pattern you look for has something that you do to that pattern. Alright, so now we're moving on to enzymes. Now, enzymes are a data structure I built to make it easier to combine patterns with their corresponding moves because they're almost always used together, similar to how nodes pair together atoms with their ports. So each of these enzymes here corresponds with the combination of a pattern and a move. And you can see here, like on this line right here, you have the prunel pattern and the prunel move used together to make the prunel enzyme. Now we're looking at the module that defines reaction sites. So when you run an enzyme on a graph, it performs a search to find all the possible sites where a reaction can occur, all the places in the graph that fit one of the patterns we defined earlier. So we build this list, and we're able to do one of two things with it. You can either take the list of reaction sites and compute each one sequentially following a deterministic algorithm, or you can select a certain random set of valid reaction sites and then compute only those. The random algorithm is a lot more interesting because it creates chaos in your program. What I mean by that is that even though you'll know the eventual result of a Chemlambda computation, if it does at some point halt, and that'll occur when there are no more sites that you can react in the molecule, the random algorithm will ensure that you don't know which intermediate steps the molecule takes to get to its final state. So yeah, each of those files, deterministic.hs and then random.hs, they each define their corresponding rewrite algorithm. So yeah, that's the chemistry module. Alright, so now we're going to move on to the language module. And this one was really fun to make because the first time I ever did anything like this, I pretty much made a small programming language for molecules. That's a funny sentence to say. But yeah, so what you'll often do in Chemlambda is have your molecules written out or encoded in text files using something called the .mol format, and I'll show you a couple of those files in a little bit. But what I did is I made a parser so that you could read in mol files as molecules into this actual program, where you could then run the computation that the molecule encoded and then get another textual output representing the result. Alright, so this next section of the code, I wouldn't really consider it much of a module in the sense that the other ones were modules. It's just more of a place where I can store sample data so that I can test out other parts of my program. So each one of these lists here represents one molecule that I can run various computations on, or just compute the molecule itself using the deterministic and random rewrite algorithms. Okay, and now on to mol files. So these are the files I was talking about earlier. This is the file format that describes a computation. And right here we're looking at the computation 4 to the power 4. I know it doesn't look like that at all, but yeah, each line in this file represents an atom that is used to make the overall molecule, which you can run using the program to compute the value of 4 to the power 4. The cool thing about mol files is that you can split a mol file at any point, and you end up with 2 separate mol files. Now that's amazing, because what that means is I can take a computation encoded in Chemlambda, which is really just a computation in general, and split it amongst arbitrarily many computers. So I can take very large computations and then compute them in a very short amount of time because I can use each computer, each unit of processing power to compute small parts, and then I can recombine all those small results to get the overall result of the computation. One of the challenges I'm working on now is to figure out the most efficient algorithm I can for splitting a molecule amongst an arbitrary number of computers so that computation can take the optimal path to completion, the fastest path. So that pretty much sums up the tour of Chemlambda-hask. There's still a lot to talk about, but I wanted to keep this kind of short. Well, 10 minutes short. But yeah, thanks for watching, and I hope you enjoyed.